Hi everybody, my name is Overtime and I want to present work done by myself and my colleague Dan Suissa under the supervision of our advisor Professor Brafman. This work is called Plug and Play Task Level Autonomy for Robotics. So our agenda today will talk about some motivation and background regarding robotics and AI planning, existing systems, the gaps we found, our contribution, a video, an illustrative example, and a summary. So the current state of affairs today. How do large companies develop autonomous robots today? We interviewed engineers from such companies. So what they first of all they develop basic skills for the robot, things like navigation, arm manipulation, object detection, and after these basic skills are implemented, then they implement a decision mechanism that schedule the different skills to achieve a high level goal, like to pick all the toys from the room and to put them inside the basket. But this is not simple. Why? Because robots are physical agents and their actions are not deterministic, and more than that, the sensors, they are limited and noisy, so when you're writing such a script, you don't fully know the current state of the environment. And even after they wrote, and it's very hard to write such scripts and they succeeded, if the environment changed, let's say the basket is now two baskets with different dimensions, or maybe the robot arm was replaced, then they need to rewrite all of this or part of it to rewrite the script. So why don't they use AI planning? In AI planning you can describe a planning problem, and if something changes, then you change the planning problem, and planning algorithms will decide on the best scheduling policy. So why don't they use it? The reason is that there is a significant integration effort, and also there is a gap between low-level robot code and abstract models used in AI planning. We think that there is a variety of different types of formalisms to describe a planning problem, and we think that POMDP is appropriate for robotics. Why? Because in POMDP you don't plan when you don't know the state of the world, but you maintain a belief state, which is a distribution over possible states. So it's good for the lack of knowledge of the robot of its current state. Also in POMDPs, each action can be probabilistic, and it's good for physical agents, because when I perform a pick, I don't know if it will be successful or not, if the object will break or not, so I need to reason about these things. And also in POMDPs, the agent, after every action, it receives a reward from the environment. So in POMDP I don't want only to reach a certain goal, but I can describe an objective function, that I don't want to be too close to people, or that I don't want to waste too much fuel. And so this expressiveness is good for real world problem, and it's appropriate for robotics, and this is our opinion. So how do we describe a POMDP? There is the possibility to exhaustively describe a planning problem, but even for 10 Boolean state variables, then the state space will be around 1000, and for a single action the transition function will be around 1 million cells in the table of the transition function. So it's not practical. What do people do? They use action description languages, as we see here in RDDL, and we can see here this is the wildfire domain. You can see in this example you have a fire that is spreading, and each of these cells has 3 Boolean state variables, and there is one action to put out a fire. The agent doesn't want a target cell to be burned, and you can see here this is how the transition function is described compactly in RDDL. So this is what people do, and we have a claim. We say that current ADLs, they are not expressive enough, at least for real world robotics, And why? I will give two examples. First of all, RDDL is very expressive, so you have if-else condition, and then also you can describe probabilistic outcomes using common distributions like Bernoulli here. But still you don't have structures like while loops. So if I want to describe something that constantly occurring until a condition is met, then I will need to use if-else expressions, and it can be large for small example and not practical at all for large problems. But I needed to describe real world problems. And also another example. In this case, the neighboring is static, so the fire can spread always to its static neighbors. But what if in my problem then the neighboring is dynamic? So this is not something I can describe in RDDL, and sometimes we do want to describe such things. Also, there is an abstraction gap, which means when the AI planner decides to select this put out action, then still I will need to write some code to translate it on how to activate a basic skill of the robot. So this is also a gap. We saw that probabilistic programming languages, they can compactly describe complex probabilistic models, and also we can see here that this is also described compactly, and this is a sort, it's similar to probabilistic programming languages, but it doesn't have the full expressive power. And what we think is needed is an action description language powered by a general purpose programming language, more specifically C++. Why? Because these programming languages are used to solve real problems by engineers. C++ is widely used in robotics. It has a large set of implemented code for constructing and manipulating data structures, and we think it's more appropriate, and we need this expressive power to describe real world domains. So today, if I want to integrate AI planning with a robotic system, an existing robotic system, then I have a few systems I can use. The first is ROS-plan. It supports PDDL. In PDDL, the actions are deterministic, so this is a limitation. If something unexpected happened, then I need to perform replanning. And they also support RDDL, but in a limited way, so they can describe probabilistic actions, but not partial or noisy sensing of the world. And this system also requires significant integration effort. We experimented, so we can say it's a good system, but it has its drawbacks. And there is the Eclipse Executive that also uses PDDL. It has a high-level predefined plan for goal reasoning. It's called a goal tree, and each goal is pursued using a PDDL planner, and by the outcome they know of the execution of this plan, then they know how to pursue the next goal, if it succeeded or not, and things like that. There is the skill-based architecture that has they propose a formal language to specify robot skills. It auto-generate code which is important to assist the integration phase, but the user still need to write some code, and also they use PDDL, which means deterministic actions. So the gaps we found, current ADLs, they are not expressive enough for real-world problems. That's what we think. There is an abstraction gap between programming planning problems which are more abstract to low-level robot code. Available systems, they require the users to write code to stitches the robot skills and the systems. And also current systems support planning models, most of them which are not with probabilistic actions, and none of them support partial or noisy sensing of the world. And we also think that a solution shouldn't be tightly bound to any specific robotic system, like ROS-plan, which is tightly bound to ROS. So what is our contribution? We introduced the AOS. AOS is the autonomous robot operating system. It's a complete methodology and tools to automatically bridge the gap between basic robot skills which are already implemented and to integrate with AI planning. The AOS is a plug-and-play solution, which means that the user only they only document their basic skills and the objective of the robot, and they give it to the system, and everything is performed automatically. The system auto-generates code that teaches their code to the system and activate the different skills to reach the robot objective based by the planning algorithm. In the AOS, each basic skill is documented in two ways. One, in a high-level way, we introduce the GSDL, which is an action description language powered by C++. So this is one documentation on what is the effect when I'm activating a skill, how it changes the environment. And also each skill is documented using an expressive abstraction mapping document, and this bridges the gap between planning model and the low-level code. How do I activate the basic skill, and how I'm translating the response from the skill to an observation that the AI planner can reason with. And also there is one environment file to document the state variables and the robot objectives. The AOS users they can activate the robot and monitor and easily monitor the robot behavior and the state. So a short overview on the system architecture. The AOS has an HTTP, a web API that exposes an HTTP interface that the user can interact with, and once the user send a request to integrate his documented code, then the system auto-generate sections in the planning engine and the middleware and activates the system. The planning engine is responsible to schedule the next skill for execution. The unifying layer, all the communication is through this component, and it stores the statistics, the inner state of the system, of the AOS. And the middleware, it listens to see if there are basic skills to be executed, and it sends the request to the robot framework, which is the functional layer. And now, by the documentation of the abstraction mapping, this is how we know how to actually activate the code. So this is used to auto-generate the middleware. And the planning engine, our AI algorithms, it is based on it's a sampling procedure. So the sampling rate, when we sample different scenarios from the environment, the sampling rate is very important. And the auto-generated code, which is for a specific domain, which was documented by the user, we can outperform generic code. We tested it; it's 40 times faster than using RDDL sim, which is open source code that was used for the international probabilistic planning competition. Let's see some experiments. Okay, so now we see we have a panda robotic arm, and in this experiment we implemented two basic skills. It's a tic-tac-toe game, human versus a robot, and the robot, one skill is to draw a circle in one of the grid cells, and the other one, it can detect when the board state changes. So we documented each skill, and we also document in the environment file the objectives, which means that it receives a reward when it reaches winning states, and a negative reward for losing, and 0 for a tie. And we can see that it acts in a sensible way, and this was very easy to document and to integrate. It took us 1 day to write the skills themselves, to implement them, and 1 day to document and to perform experiments. This here is the armadillo robot. We have a real one in the lab. This is a gazebo simulation. In this experiment, unlike the first one, the actions, they are not deterministic, so we need more expressiveness to describe them. The pick action is probabilistic. It can succeed or not. It can drop the can, and it can fail and miss the can. And we describe all of this in our documentation. And the robot is supposed to serve a can to the human. And we saw that we can describe more complex behavior of basic skills. So let's see an illustrative example. This is just to get the look and feel and to see how much this documentation is expressive. There is a robot with a single navigation skill in this example, and it needs to navigate as fast as possible to 3 known locations. Now this skill can fail with a 10% chance, and when it fails, it only in 80% of the time it reports that it fails. Otherwise it will report it succeeded. Let's start bottom up. This is our abstraction mapping, and in here we connect the low-level code to the system, to the AI planning phase. We have 2 possible observation, which is success and fail. These are the abstract 2 outcomes of performing this skill, and to decide which outcome is sent, we have a concept called local variables. Now these local variables they live only for per a single execution of a basic skill, and they can take their value either for high-level parameters, variables used in the AI planning model. They can take values from there, and then these values can be used to explain how to actually activate the code. Here in the model activation, we're activating a ROS service, and these are the details on how to activate it, and we're taking information from the planning model described, which is more abstract. And also we can describe local variables that they take their information, they listen to information, public information in the robot framework. In this case, it listens to a ROS topic. It's public information published by processes in ROS framework. It's a robotic framework, and in here we describe a condition. This is Python. We describe a condition that if the input sent by this topic, if the string contains goal reach, then this variable receive the goal reach is true, and then we can say that we are sending that this action was successful. So this is how we connect it, and we can also take information from the response from the robot skill itself, and this makes the documentation very flexible on how I'm translating low-level code to the abstract level of AI planning. This is the environment file, and in here I'm describing that I want to reach the 2 known location. This is the JSDL file describing the behavior of the basic skill of navigation in a high level. So it receives a parameter, the desired location, and in here we're describing that in 10% of the chances it fails. So then the location becomes unknown when it fails, the robot discrete location. And also I'm describing the model response, which is a saved word, and it receives, we describe here noisy sensing. So we are saying when it fails, then 80% of the chances it returns that it failed. Otherwise, it is successful. And I can also describe the reward, which is the reward model for this basic skill. And I can describe that the cost here, what is described, that when I'm losing my orientation, then I'm receiving a penalty of -5, and otherwise it's the distance function from where the robot is to where it wants to be. Everything here is in C++, and the fields themselves, this is a JSON format. Summary and future work. So the AOS is a complete set of methodology and tools to bridge low-level implemented basic skill to AI planning, and this is a plug-and-play solution. we introduced the GSDL, which is our action description language powered by C++. There is the abstraction mapping to document the bridge and bridge the gap between low-level code and AI planning. For future work, we want to perform a user study on the AOS and to implement a single development environment for user using our systems to support multi-agent planning. There is work done on anomaly detection, and we want also to improve documentation based on the robot experience. And that's it. Thank you very much.